Well, hello there, fellow forum dwellers. It is Dark Java Dude 64 here. I'm not sure if any of you have ever heard me talk in a video before, but I guess now you have. And so here I shall be presenting the video of this logic gate that I built out of cardboard and thread and some beads as well, that I've been talking about for the past few days. Why is it pink? That's just the material I had. I kind of sabotaged this notebook right here, which is pink because I like pink, because pink is a wonderful color. Um, okay, so this here is a logic gate. I'm sure probably a good majority of you are familiar with logic gates and what they do and such. They're very simple if you aren't, but I'm pretty sure the majority of you are familiar with what they are. This is a AND gate. Yeah, so this is a logical AND gate, and as such, it has two inputs, which are these two side strings right here, and then it has an output, which is this one center string right here. And then I've put these little tape flags on it to kind of mark where it is. So of course, both of the inputs and the output can each hold one of two positions. They can either be in the low position, which they're currently in, or they can be moved up to the high position and back down to the low position. I can move the output, or I'm sorry, the other input up to the high position and back down to the low position. As you would imagine, the output, this being an AND gate, this output here should move up to the up position only whenever both of these inputs are at the up position, but otherwise it needs to be in the down position. So I will demonstrate that. As you can see, it currently is indeed in the down position because the two inputs are in the down position. If I place one input in the up position, the output remains down, just as it should. If I put the other input in the up position, the output remains down, just as it should. But if I raise both inputs, you can see that the output also raises exactly as it should. And if I lower either input, a little tricky sometimes. If I lower either input, it pulls the output back down with it. So yeah, so that right there demonstrates the basic functionality of this logic gate and the fact that it works and such. Let's see, I think I first pulled it up with, oh, I forget which, but yeah, so I'll just reiterate. I can lift up one side, and tape is kind of sticky, and pull up the other side, and it goes up with it. And I can lower either one of these, and the output goes back down as it should. Let's see, I can raise this one, and then as this one goes up, the output goes up with it. And I think you get the idea. It is a little bit finicky sometimes. Go back down. There we go. Okay. What you see right here is not the actual mechanism. The mechanism is on the other side. And it is really, really simple. It's just, I think it consists of like 5 separate sections of string. And it really is a pretty simple contraption. I've used beads in pretty much everywhere a place that two strings tie together, which at first I thought was necessary because the first logic gates I built several months ago were made of like twine. It was like a thicker kind of cotton string, and with that it had slipping issues whenever I would tie two together, and so using beads to tie it together made more sense. But I found that with thread here that's actually not necessary. The problem with beads is that they okay, so because this whole mechanism works off of a specific geometry, I want all the different pieces to be the to be the correct length and such. These beads kind of introduce a little bit of give and allow the geometry of the mechanism to change a little bit, which can therefore change the functionality, which is one reason why the output doesn't really move as far as the inputs move and such, which it should. It just doesn't because these beads introduce some variability of the geometry of the mechanism, and that sort of impedes on its functionality a little bit, unfortunately. But I think in the future, when I make these, I'll just exclude the beads. There is one bead right here that is necessary, and it is the reason that I bought these glass beads. I bought this whole package of little tiny glass beads. It is an absolute wonder that they haven't gotten everywhere, especially with a cat around. Although I keep them in a pretty safe place. Oh, and then just to show you, thread. Cool thread. Yay, cool thread. where was I? Oh yeah, so this bead right here, this is basically a place where two strings rub over each other whenever the output is being raised. In fact, this point right here is actually where all of the mechanical energy used to raise the output when necessary. That right there is the point it all goes through. And traditionally, you basically had two strings that were kind of rubbing against it. It's sort of hard to visualize it, but you had two strings rubbing against each other. So I figured that if I just put them both through a glass bead, that would greatly reduce the friction. And as far as I know, it has indeed reduced the friction, which is good, especially if I want to build more complex mechanisms where you have one logic gate connected to another, so on and so forth. I think it'd be really cool to build like a full adder, or like a 2-bit adder or something like that. That'd be kind of cool. Maybe even a computer, although that's sort of lofty and that sounds kind of impractical. But I'm not sure. But yeah, again, it is a really, really simple mechanism. One of the things that I really like about this whole logic gate mechanism, well, okay, there's a few things. Each bit is effectively conveyed by two strings in a bit of a pulley system. So as you notice here, whenever I raise one of the inputs, you actually have string going in there, but coming out of here. So what that means is that, in effect, each bit is carried basically by two strings that work in tandem. And of course, as one string goes one way, the other string goes the other way. This is really, really nice because what it means is that whenever I connect the output of one logic gate to the input of another, I can simply just flip the strings and it actually simulates a NOT gate in between those two gates. So this is nice because this here is an AND gate, but if I flip it upside down, and this is kind of cool, it effectively becomes an OR gate. If we now assume that this here position is our down position, we can now see that if you raise one input, or the other input, or both, our output raises as well. And that right there it follows the truth table of an OR gate. So that's kind of cool. So I have an AND gate here, and if I flip it around, which is the same thing as simply just flipping the connections of all of these strings here, which effectively just puts a NOT gate on both of the inputs and the output, that turns it into an OR gate. So this is great because now I have an AND gate, an OR gate, and I can create NOT gates whenever I want to. Whenever I'm connecting two gates, I simply just flip over the two cables and I get a NOT gate. And from those three gates, you can build any logic circuit at all. So this is a really neat mechanism. So yeah, thank you for watching. If you've watched this, I guess that's kind of a brief overview. I didn't really explain how it works. I guess I could if any of you were curious. But yeah, thank you very much for watching.